you, Carlos. So, good afternoon, everybody. It's really a pleasure to be here. And first of all, I would like to thank Rudy and Carlos for putting up such an exciting meeting and for giving me the opportunity to participate actively to the meeting. Is it working? Now? Working? Okay. So there is some... Yeah. Okay. So, I'm going to talk about the BCS BC crossover in 2 dimensions and the polaron to molecule transition in 2D. And before starting, I would like to acknowledge the person who did most of the work, Gianluca Bertaina. So he was a PhD student, a former PhD student in Trento, and now he is a postdoc fellow at the École Polytechnique in Lausanne. The theme of the talk is BCS BC crossover. We all know that this subject has been investigated very extensively in the last, let's say, 8 years, both experimentally and theoretically in 3 dimensions. And the reason being that it's a fundamental paradigm in the physics of pairing because it allows us to join together the description of a BCS superfluid to the one of BC superfluid going through a highly interesting regime that is the unitary limit where the behavior of the system is universal and has many analogies with other very different systems in nature, like the quark-gluon plasma and the neutron matter in the crust of neutron stars and other systems. So it's really highly interesting. So a natural question then arises as to what happens to the BCS-BC crossover if one reduces the dimensionality. And so, for example, in 1 dimension, in 2 dimensions, we know that the role of both thermal and quantum fluctuations is enhanced. And then we also know that off-diagonal long-range order is suppressed at finite temperature, and the superfluid transition is of the Brzezinski-Kosterlitz-Thouless type. And so there are qualitative differences compared to the 3-dimensional case. And then the 2D case could be also relevant to understand better pairing in high TC cuprates, where the 2-dimensional character seems to be crucial. And because of that, of course, there has been in the last 2 or 3 years a lot of intense experimental activity. Probably it started in the group of Turlapov. They were probably the first to have a 2-dimensional interacting gas. Then Cambridge in the group of Michael Köhl, the group of Chris Vail, Martin Virland here in Cambridge, Massachusetts, and then the group of John Thomas at Duke. And then probably this is not a complete list of groups interested in the 2-dimensional Fermi gas. So before I would like to draw some, to understand better what are the analogies and the differences from compared to the 3-dimensional case. So if we are in 3D, then the scattering at low energy is described by this formula here, where A3D is the scattering length. So we see that if you are at low energy, actually the dependence on the relative wave vector disappears, and you are left with a constant. And then even more interesting, if you are in this regime of relative wave vectors between the inverse of the range of the interaction and 1 over A3D, the dependence on the interaction disappears completely from the scattering, and that's the famous unitary limit. So there is no equivalent to this in 2 dimensions because of this logarithmic dependence on the relative wave vector. So there is always a dependence on the energy, which means that there is always a dependence on the density of the system. And in particular, there is no equivalent to the unitary limit. So there is no regime where the scattering amplitude is independent on the interaction. Then another difference is that in 3D, there is a bound state, of course, if the well is deep enough, which is given by this formula. And in 2 dimensions, instead, a bound state exists for any depth of the well. And, but then the dependence on the scattering length is similar. So here I just mentioned that according to our definition of, so there is a little arbitrariness in the definition of A to D. And so we use the definition, this definition, which is the, if you go to a repulsive gas, then in the limit of a hard wall disk is exactly the diameter of the disk. But there are other definitions which include this factor 4 and e to the 2 gamma, and so in such a way that the binding energy is has exactly the same form as the 3D binding energy in terms of the scattering length, but the two, of course, are equivalent. Then, okay, so the unitary regime in 3 dimensions corresponds to when the bound state appears. And in that case, you have an infinite scattering length. But of course, in 3 dimensions, this happens when interactions are already quite strong. In 2 dimensions, instead, the infinite scattering length regime happens when interactions are really, really weak. And so you are in the deep BCS regime. Another thing concerns the coupling constant that, okay, in 3D is proportional to the scattering length and, of course, diverges approaching unitarity. In 2 dimensions, the coupling constant depends logarithmically on A to D. And, okay, so if you want, it diverges if A to D is comparable to the inverse of the Fermi wave vector. But this is true only with logarithmic accuracy, of course. Okay, so once we understood that, in any event, we have also in 2 dimensions a BCS-BC crossover, because so if you imagine that you start with such a macroscopic Hamiltonian where you have a balanced configuration of up and down, and this is the kinetic energy of the up and down component, and here is the interaction potential between the up and the down, which we model by a square well, for example, with a very small range in such a way that finally all the results should be completely independent of the range R of the interaction. So imagining that you fix the range and then you play with the depth of this potential, that's the behavior of the 2-dimensional scattering length in units of the range R. So if the depth of the well is very small, you are in the BCS regime where A to D is really large, and you have a weakly bound two-body, a weakly bound dimer. Then, okay, at some point, so instead, if you make the depth large, you enter a regime where A to D is smaller compared to the 1 over KF, which is shown here, and then this is the BC regime. And of course, when A to D is on the order of 1 over KF, you have the crossover regime of strong interactions. Okay? So now, how can you realize this in experiments? Of course, you have to make sure that your system fulfills 2-dimensional kinematics. So if you have a thermal gas, you have to ask that the temperature should be much smaller than h bar omega z. And so if you are at low temperatures, lower than the Fermi temperature, then you should ask that the Fermi energy should be small compared to the transverse confinement. And then once you have fulfilled the 2-dimensional kinematics, then, okay, if you are interested in scattering, then there is a very nice mapping from 3D to 2D that allows you, once you know the 3-dimensional scattering length and the strength of the transverse confinement, allows you to obtain the effective 2-dimensional scattering length. And then this works well for any value of A3D and AZ, provided you are interested in scattering. Instead, if you are interested in the molecular state, then okay, you have an additional condition that asks that your description of the molecular state is correct in 2 dimensions if the binding energy of the molecule is much smaller than the transverse confinement. Otherwise, you enter a regime of quasi-2D where your molecule is no longer the purely 2-dimensional molecule and contains some effects due to the confinement. Okay? So we will be always in the regime of purely 2-dimensional situation. Okay, so let's see what the simple mean field theory tells us, at least concerning the 0 temperature. This was worked out back more than 20 years ago by Randeria and co-workers. So if you start from a simple Hamiltonian with a coupling constant, and you work out in the usual way the gap equation and the number equation that allow you to solve the BCS equation, where here is the quasi-particle dispersion. The nice thing about 2 dimensions is that those equations can be solved analytically. And so then the result is that the chemical potential is just the Fermi energy shifted by half of the binding energy of the molecule. And the order parameter, delta, is just, again, related very simply to the 2 energy scales, epsilon f and epsilon b. Of course, here, the Hartree term that you have on the BCS side are completely neglected. And also, you can see that you lose completely the physics of composite bosons, because once you go to the deep BEC regime where the binding energy of the molecule dominates, the only correction is, there is nothing that tells you that you have composite bosons that repel each other with some coupling constant. Okay? So then the mean field captures more or less qualitatively the behavior, but of course quantitatively is completely a different story. And okay, so what we do is we do fixed node diffusion Monte Carlo, which, okay, so I will not explain the details of the method. It is a very, very well established technique that works for fermions at 0 temperature. And the idea, of course, in the case of fermions, you cannot be exact. So diffusion Monte Carlo is exact in the case of bosons, of the ground state of bosons. In the case of fermions, it's not, because you have the problem of the sign, the famous sign problem. But so the fixed node allows you to overcome this problem by doing an approximation. In a way, what you do, you fix the nodal surface of your many-body wave function, and then you do a calculation with this nodal surface fixed. And so it's a sort of variational method, not in terms of the wave function, but in terms of the nodal surface, which is much, much better. And so here are the results for the equation of state. Then I will show you results about the superfluid gap and probably also about the contact parameter, depending on time. So concerning the equation of state, so here is your interaction strength, which is conveniently written in 2 dimensions in terms of the logarithm of kf(a)(2d). And so here is the BEC regime, and here is the BCS. Okay, so you can see here the dashed green line is actually the binding energy, so half of the binding energy. And so you see that our results in the deep BEC regime go over to the binding energy of the molecule. And the dashed blue line is instead the mean field result. That is always a little higher compared to our Monte Carlo results. And especially in the BCS regime, you can see that it doesn't account at all of the Hartree terms in the Hamiltonian that give you an attraction. Okay, so but you can see that the mean field result gives you more or less qualitatively the proper behavior, but you have important deviations, and in particular, this is better understood if we go a little bit further in the analysis. And for example, okay, so on the BCS side, one can do a perturbation expansion. This was carried out by Bloom and Engelbrecht and Randeria again. so especially the second paper is the one that got the coefficient of the beyond mean field term correct, and that's equivalent to the famous paper by Li Wang that gives you the corresponding expansion in 3 dimensions. Okay, so here you see that to lowest order in the interaction strength, you have the Fermi energy, so that's the energy per particle. So you have the Fermi energy divided by 2, and then you have contributions that are proportional to 1 over the logarithm of the kf A2D. But even more important is what happens on the BEC side, where, okay, so here what you should recover is the equation of state of composite bosons. And then if you take the energy divided by the number of dimers, okay, so you have the main contribution is the binding energy of the molecule. But then here you have the equation of state of bosons, which interact with a scattering amplitude that is given by this AD square, AD, that is the dimer-dimer scattering length. So this looks very ugly. But the reason why one should include also the beyond mean field corrections is in order to obtain also the proper coefficient in front of AD. Because if you since you have a logarithmic dependence, if you change by a proportionality constant AD, then this will reflect in some coefficient here. So the beyond mean field corrections are necessary if you want to pin down what is the proper value of the dimer-dimer scattering length. Okay, so if you now go to the same equation of state, but you subtract the trivial contribution coming from the molecule, then so the mean field result would be 1. Okay, so that's the Fermi energy, and instead we see this behavior here. That here contains all the physics of the Li Wang expansion that is shown here as a orange dashed line, and here instead it contains the physics of the composite bosons that is shown here. And from our fit, we get a dimer-dimer scattering length that is 0.54 A2D, that is in agreement with the result obtained by Petrov and Shliapnikov. Okay, so that's very, so by coincidence, that's very similar to the 0.6 that also is the proper result of the dimer-dimer scattering length in the case of 3 dimensions. But okay, so this number here actually depends a bit on how you define the 2-dimensional scattering length. So, so again, this is the result where AD is the diameter of hardcore bosons. So okay. So concerning experimental relevance of these results, there was this recent paper by the Melbourne group where they measured in situ the density profile of the Fermi gas along the crossover. So here is the BCS regime, and then you move towards the BEC regime. So one important thing that one should notice is that if one believes in mean field, then the density profile should be always the same and the non-interacting one, because the chemical potential, I remind you, is binding energy of the molecule plus epsilon f. So the binding energy does not depend on density, and so the density profile, if you use local density, is just fixed by epsilon f, by the Fermi energy of the gas. So it should be exactly the same in the whole BCS-BEC crossover. So the fact that they see instead moving towards the BEC a shrinking of the cloud is an evidence of beyond mean field effects. And so here they compare the profile with a result that they obtained from by fitting our equation of state, and also the result here is obtained by using our equation of state to determine the mean square radius of the cloud. And so there is a good agreement in the profiles, actually, especially on the BCS side. So there is a little discrepancy that is probably due to temperature effects, okay, because so they cannot be so sure about the temperature here. Okay. Now, okay, so the other thing is the gap parameter, so the superfluid gap that we also calculated. The way we calculate it is by looking at the energy of the system with one plus and one extra particle in in one component and one less particle in the other component by using this this formula here. And again, we should compare with the mean field result. So the mean field theory gives you that the superfluid gap is actually the order parameter if the chemical potential is positive, and then is just, again, binding energy divided by 2 plus Fermi energy if the chemical potential is negative. Okay, so here are the results for our calculated gap compared with mean field. Again, so for this quantity, if you do nothing, so you see a very good agreement with mean field. But then again, so there is a trivial component to it, that is the binding energy, and if you subtract the binding energy, then you see large deviations compared to the mean field. So in the region where the chemical potential is negative, so in this region here, the mean field result predicts just epsilon f, and here instead we see a gap that decreases to small values on the BEC side. So here I would like to make a remark concerning the experiments carried out both at MIT and Cambridge with radio frequency spectra, where they measure, what they measure is the difference between the excitation spectrum at k equals 0 and the chemical potential. So, of course, we did not, in principle, one could use quantum Monte Carlo to calculate this quantity, the chemical potential and the spectrum at k equals 0. We didn't do that, but at least in the regime where the chemical potential is negative, the value of the excitation spectrum at k equals 0 coincides with the gap. And so what is measured is actually the gap. So if mu is negative, the gap minus the chemical potential. So of course you see that in both in the gap and in the chemical potential, the main contribution is the binding energy, and the two come with different signs, so they sum up, and you have the binding energy. And then in principle, you have beyond mean field corrections, because at the level of mean field, you have a Fermi energy here, this one, and a Fermi energy here, and so the two cancel, and you are left with the binding energy. And this was the result obtained by Marty. Here, in principle, you have beyond mean field corrections, but the problem is that the two have the same sign. So you see that the deviation compared to binding energy divided by 2 in the gap is this, which is a fraction of the Fermi energy. And if you go to the previous slide, okay, so here is energy per particle, but chemical potential is similar. So what remains once you subtract the binding energy is also something that is very similar to the other one. And so once you take the difference, the two things almost disappear. And so you have a very little effect. So then the message is that if one wants to point out beyond mean field corrections, one should be able to measure the two quantities separately and not take the difference. Okay? Okay, so here is the, how am I doing with time? Okay, so then I can probably also talk about this. So that's another thing that we calculated. That's the contact times parameter. This was measured in 3 dimensions by first back in 2005 by in the group of Randy Hewlett. Then probably, so here I missed somebody. So but there was the work at Gila and also the work at again in Australia. So what we do here is try to calculate this contact parameter as a function of the interaction strength in 2 dimensions. So according to the paper by Ivan Kasten and Felix Werner, in the same way as it is done in 3 dimensions, the contact parameter C is related either to the derivative of the equation of states, and here you can write it in terms of the derivative with respect to your interaction parameter, that is the log of kf a to d, or is also the coefficient in front of the logarithmically divergent term in the pair correlation function of up-down particles. So in 3D, this so the first definition is very similar. Just here you have kf a to d, and of course in 3 dimensions the pair correlation function diverges as 1 over r squared, and is the coefficient of the 1 over r squared. Here instead diverges as the logarithm squared of r over a to d. So on one side we can extract C from the short-range behavior of the pair correlation function, so the slope of this function here, or we can differentiate our equation of state. And here are the comparisons. So the line is obtained from the equation of state, and instead the points are obtained from the short-range behavior of the pair correlation function. So again, if you look here, they seem to agree very well. But again, as usual in 2D, so there is a trivial contribution. Okay, there is a trivial contribution that comes from the bound state. That is this term here, which just comes from when the energy is the binding energy of the molecule. So that's a trivial contribution. And then if you subtract this trivial contribution, you can point out more significantly many body contributions to the contact, and the result is shown here. And so we see that in this region here, our wave function is probably not the best that we can have in order to simulate the system. So one could probably improve considerably our nodal surface in this region here. Okay. But in principle, we have the complete calculation of the contact parameter. Okay, so now let's go to the last part, probably a couple of minutes, and it's the polaron versus molecule problem. So in 3 dimensions, there have been many experiments at MIT and ENS, and the problem was, I would say, finally solved theoretically by the contribution of Prokofiev and Zvistunov, who carried out diagrammatic Monte Carlo. So in 2 dimensions, there are experiments that are carried out now in the group of Martin Zwirlein, Michael Kohl, and John Thomas. And there have been a lot of theory papers. Probably I'm not listing here all of them, so I'm just, so those are the ones that probably I came across first. Okay, so of course all these theory papers are using either mean field approaches or variational approaches. So we would like to do something better using quantum Monte Carlo. So in from our point of view, the description of the polaron and the molecule is something that reflects in a different choice of the nodal surface, and so a different trial function. So the polaron, we describe the polaron by a Slater determinant of the n-up fermions. That's a usual Slater determinant made up with plane waves, which satisfy the periodic boundary conditions in the box. And then you have a Jastrow term that couples each up fermion with the impurity. Okay? So here you have, so the nodal surface is fixed by the nodal surface of the Slater determinant, that is the nodal surface of a free gas. And so and this describes our polaron. Instead, the molecule, we construct a determinant where you have, so the impurity is coupled to each of the up particles, and then all the rest of the up particles are occupying plane wave states. So it's clear that the nodal surface here and here is different, and so, of course, we get different energies if we compare the 2 results. So first here I show the result of just the polaron. So those are the green results, and I compare them with the binding energy of the molecule. So of course, and you can do here a perturbative calculation, and we see that in the limit of weak coupling, we recover exactly the perturbative result. And okay, and instead here we show the comparison between the polaron and the molecule. Again, if you subtract the binding energy, because okay, so especially in the BEC regime, it's clear that if you add one impurity, then your energy will be the energy of the non-interacting gas plus the binding energy of the molecule minus minus epsilon f up, because you have taken one particle from the up Fermi sea and you made a molecule. And okay, so here you see the results. So here is the region where the polaron is more favorable, and then at about 18 epsilon f, you have a transition to the molecular state. Okay, so so since the transition happens at such large values of binding energy, so it's clear that here beyond two-dimensional effects are very important, because usually, so there is a factor 10 usually between the Fermi energy and the transverse confinement, and so here you have a binding energy that is 20 times the Fermi energy, meaning that is already on the order of the transverse confinement, meaning that the two-dimensional description of your molecule is no longer valid. And so these results only apply in a strictly two-dimensional case, which is probably not the case in experiments. Okay, so I'm done. Okay, so concluding, so I presented you the first quantum Monte Carlo study of a strongly interacting two-dimensional Fermi gas, and we calculated the equation of state, the gap, the contact parameter, and we also considered the polaron problem. Future perspectives here, so one could investigate what happens going from the single impurity towards an imbalanced gas. And then also one possible, one interesting question could be whether the two-dimensional configuration helps in obtaining ferromagnetism. And so the issue whether the Stoner instability could be stronger than the pairing instability. That was the problem affecting the situation in 3D. Okay, so with this, I just conclude, and thank you for your attention.
So we open for questions.
So the mean field theory of Randaria, Engelbrecht, and also our chairman is based on a Bogoliubov channel decomposition. Yeah. So I'm wondering, does there exist a more sophisticated mean field theory where also the Hartree and the Fock channels are taken into account, which may be relevant for at least higher temperatures?
I'm not... so you mean something similar to what is done in 3D, so the Nozière-Schmidt-Rink approach? So I'm not aware of...
Just ask.
So I probably...
partially that.
Yeah.
There's some improvements, but it's still more work to be done. I mean, the way it works, you have to couple that a little bit with some kind of RG approach in order to get the BKT transition. Because the transition will be determined by an accurate calculation of the superfluid density and how it changes across the phase boundary line. So you can do mean field plus the Koslitz-Towles type condition, and then you get something, which is reasonable but not the best. But anyway, any more questions that we can ask?
How well does the variational ansatz work for this 2D case? So did you compare with the...
Yes, I think it should work very well. So we probably didn't yet compare in the whole range. But so you can see here, so that horizontal line is the value. So here is called ZBP, that is Zollner, Brun, and Pettig. So that's the value, the asymptotic value that they obtain in the deep BEC regime. So we seem to agree with this, but we didn't yet compare the whole curve. But I would expect that should be.
There is calculation by Mera Parish. I think she calculates the crossing as well, and so
yeah,
she has the energy of the molecule.
This happens at much smaller values, around 6 here.
Okay.
Yeah. So yeah.
I know they cross very. The crossing is very shallow, correct? It's very.
Yeah.
Okay.
Yeah, so we get it around 18, but we are still improving, so we are having some more points here. And so, but then again, this is probably something that is not relevant for the present generation of experiments because the value of the binding energy is too large.
Can you actually calculate or derive both quasi-particle residue and effective mass in these calculations for the polaron? Because this should be measurable. I mean, somehow
so effective
they have
mass
been
we
measured.
don't because it's a bit too complicated, but we do have the quasi-particle residue. That I don't have it here, but I received it just a couple of days ago from Gianluca. So we do have it.
And I noticed you had 2 sets of points on the BCS and on the BEC regime, so color it differently. Do you use different wave functions?
Yeah,
or?
so so that's actually something more technical. Yeah, so it's actually okay. So the black points are using a sort of BCS type wave function that is similar to the one for the molecule, okay? But now is constructed for a balanced configuration. And so this wave function is how do you say? So it's compatible with off-diagonal long-range order, okay? Instead, so if you go to the BCS regime, it's very difficult to calculate correctly the order parameter because the size of the Cooper pair or analog of the Cooper pair becomes very large, and so your box is finite and it's very difficult. So, but then, okay, the argument is that the contribution to the equation of state is exponentially small. And so instead we used a wave function that is not compatible with off-diagonal long-range order. That is the wave function of 2 Slater determinants. Okay, but then the argument is that concerning the energy is correct. Okay, and those are the points, the gray points. Okay.
Do you think that the presence of a minimum in the curve, the polaron, when you subtract the binding energy is physical? Or do you have, okay.
So
can you comment on
that? I think that, yeah, so here you are subtracting the binding energy. So it just is how it compares with the binding energy. So there is no reason why there shouldn't be a minimum. And so we now would like to check with the variational wave function, say the single particle Hall wave function, and this probably will also have such a minimum. In a way, it's similar to what you were showing yesterday.
Yes. Any more questions? So I just make one short comment. I think mean field plus fluctuations also do not do a bad job actually with those corrections. It's a bit harder, but.
Yes, so this was used in 3 dimensions. Was used quite
systematically.
At finite temperature and also at 0 temperature. Yeah. So here I concentrated more on the 0 temperature. So I'm not very updated with all the contributions at finite temperature, but I think that can be used.
Well, actually, it's to Carlos. Since you mentioned that mean field plus fluctuation works pretty well also in 2 dimension, I just want to understand, not far from the critical temperature. I mean, because fluctuation give a divergent contribution, right? In 2D. If you do Navier-Schmidt ring in 2 dimension.
No, you have to do the RG.
Ah, the RG. Okay. Okay.
Yeah, no, by itself. Yeah. But I'm saying at low temperatures you can do the same kind of analysis also, and it improves a lot the results. Anybody else? Questions? No? Okay, so then we can move. Thank Stefano for the very nice talk, and.